Thanks for coming. So I've got a little frog in my throat today. So hopefully it lasts for the whole lecture. The camera's close, and most of you are in the front half, so that's probably good. So before we get started, we're going to talk about like a third kind of big class of clustering today. But before we get started, let's talk a little bit about some of the kind of administrative things. So first, I have to leave just after the lecture ends today. There's a PhD defense I have to run to. So unfortunately, I won't be around really for questions much after class, maybe for 1 or 2 minutes, but not longer after that. So where are we on here? So we're finishing up the clustering part of class. We've actually covered a lot in clustering, and I'll use the first part of the lecture to kind of review all the things we've talked about so far. I mean, there are other types of clusterings that we haven't talked about, but this is kind of a pretty good cross section of what the general type of techniques out there will have seen. And then you'll get to play with a bunch of those in your homework, which is posted as as well. Then the day collection report for the project is your second milestone, and that is due on Wednesday. Okay, so this is one of those parts of the project where I'm just kind of making sure you're making progress on it, so you don't do it all at the very end of the semester. So if you kind of fulfill the requirements, you'll get full points on this. But just to kind of make sure you're keeping moving on this, we went over this before, but just review. There are always questions. What I'm looking for, basically, to get a sense of your data, kind of to force you to try and find the data that you're going to work with this point, right? So you should have explained how you got it, how large it is. You should try and download it. Or some of you are like scraping things, say off of Twitter, and you should kind of try and give me evidence that you've started scraping them. Because if you wait till the last minute, you won't have the data, and if you don't have the data, you can't start trying out techniques and so forth, right? Okay, and then kind of after that, what format are you storing this in? Again, this is from these abstract types like a vector or matrix, or it's text, and you're storing as text with maybe some metadata on top of it, or you're going to convert it into something else. Maybe you haven't quite done that yet, but you have a concrete plan of at least the first thing you're going to try here. Or it could also be a graph, and we'll talk about graphs today. Okay. And then kind of a question about, do you need to process this data? Just kind of a continuation of the third question. Sometimes the answer is no. Sometimes it's yes, and that'll indicate, well, this will be a larger fraction of your project than other groups where they just can download it in the perfect format already. And then the fifth question, how you be able to simulate similar data, something that I think is really important and always comes up, because if you haven't gone deep into this yet, this is kind of, it's not very obvious, but I'm going to ask you to kind of have some, hopefully, kind of real-world-ish data set you're going to try and run something on, but that's going to be, maybe it's only one data set, right? It might be a few data sets if you're lucky, but for a lot of you, it'll be just a single data set. Whereas you might want to say, well, there could be lots of types of data sets. There could be a variety of how clustered is the data, or how strong is the regression analysis, how kind of structured is the graph that I'm building. And so you might run your algorithm and it works well or it doesn't work well in the one data set you have, but if you have other data sets, you can kind of do some more kind of try more variations in the data and something where you know there's going to be a structure there, right? So how would you do that? And this varies very broadly across the different sorts of kind of problems you might have, but just kind of, you want to say, if I'm trying to find clusters, how do I generate data set that looks kind of like the one I have, but I know have clusters because I put them there? Okay, so that's kind of like, how would you do something like that? And I don't necessarily need a perfect answer there. Again, if you write something reasonable, you'll get full points, but I want you to think about this. It turns out to be a very useful exercise, I think. All right, so okay, and you should all have groups formed, right? And that should be all set in Canvas, so each group, only one person needs to turn in some document, right? So it's 1 page per group. Okay, so it should not be a very kind of onerous thing to write stuff up, but it's just forcing you to have progress along the way. Does this sound good? Great. All right. Crash. Okay. All right. Okay. Good. So, plan today is to talk about spectral clustering. So there's this kind of so there's this famous paper that there's this famous paper that has a title so it's something like good, so good, bad, and so spectral. Whereas it kind of arguing kind of in a like not 100% serious way, kind of joking, but that in clustering there's the good clustering, there's bad clustering, and then there's spectring, which is this different class of clustering, right? That's so it's like a very different way of thinking about it. And I'm going to try and this was the perspective in our early days when people were studying this sort of clustering. I think now we kind of think of more of it in more of a holistic framework of like where it fits. And I think ultimately the sort of answer you're going to get from clustering is from spectral clustering is not that different from the other sorts of clustering that you get. So for instance, there have been some, like we talked on Monday about Kmeans clustering problem, right? And we mentioned how there is this Lloyd's algorithm for Kmeans, but the Lloyd's algorithm is not guaranteed to actually work. Sometimes with Kmeans++, you can initiate it and then you have some sort of guarantees, but they're a little bit looser than you might want kind of in a total theory setting. And so people design things where they say, well, I'm going to come up with an algorithm that has guarantees to find the right answer, and that usually involves spectral clustering as part of the solution. Okay, so it's end up linked to K-means in various ways. All right, so we've talked about this idea of clustering where you have this data set and some distance, and so what you wanted to do is to break this up into these subsets, which are each these going to be these subsets of the data set X, right? Which is usually a disjoint partition, although in some cases you don't have to include all the points, say if they're outliers, or the clusters could overlap with each other, and there are a bunch of variants of this as well. Okay, and so we've talked about these two frameworks. So the first one we talked about was so was this hierarchical agglomerative clustering, and and what this did is, if you remember, you had these data points, and it's kept grouping them together, and then group together these whole clusters, right? And what you can think of living on top of here as is some tree, and so it gives you this hierarchy over the data sets and this clustering. But what this, when I look at this agglomerative term, agglomerative means kind of glomming stuff on, or it's kind of building up, right? So it's starting from the bottom and it's building up the hierarchy from the bottom. Okay, it was kept saying what's the best way to merge together two clusterings, and this told us about what the general form of the procedure that we used. Okay, and then the second form of clustering that we talked about was the assignment-based clustering, and so this started with some data, but the key here was that I identified these points, these representative points, and this basically implied this partition of the space, right? So there was this underlying Voronoi diagram, which was like the bisector between the centers, but kind of extended to kind of decompose the space. And the clusters was defined implicitly based on these centers. And you could define these centers in different ways, either to minimize the sum of the square distances, this was Kmeans, or the worst case distance, this was K-center, right? And there were different variants of this we talked about. I'm going to start this lecture by kind of give a little perspective on there are a few pieces of this puzzle which I want to there's a few more things I want to say about this. Okay, okay, but to give the context, the third way of doing this is is spectral clustering. Okay, and spectral clustering is going to give us a hierarchy. Okay, so it's going to give us a hierarchy like the hierarchical agglomerative clustering. So it's not going to be center-based, but it's not agglomerative. It's not building from the bottom up. It's going to be partitioning by doing, but it's going to do this in a way that's kind of so top down. Okay, so what I'm going to do, I'm going to have this data, right? So say my data looks like this. The first step of spectral clustering is going to find a partition between the best separates the data into two parts. Okay, and then it's going to recursively do this on each part, and then keep partitioning this tree from the top down instead of from the bottom. Okay, so the key is to figure out, I've got one data set, I need to split it into two parts. What's the best way of doing this? Okay, whereas the hierarchical agglomerative clustering was, I've got a bunch of data sets, I want to figure out how to merge them together. This is more of a top-down approach instead. Okay, and so that's kind of, from a very high level, that's the different way of doing this. Okay, and so there are other ways other than spectral clustering which do a top-down so partitioning of the data. For instance, you can use assignment-based clustering, kind of run the Lloyd's algorithm with k equals 2, right? This will give you a partition. It'll give you two centers, and then I take the dividing line between the two centers, and this divides, and then I do this recursively. Okay, so this would also work, and this is an alternative in how to do this. The spectral refers to using like an Eigen decomposition. Okay, so we're going to transform stuff into a matrix, and then we're going to do an Eigen decomposition, and this is going to encode the best way to partition the data. Okay, so that's what the kind of the high level view of what we're going to do. I'll explain how we get there. It'll take a few steps, but that's kind of the idea of spectral clustering. Yeah.
Is spectral clustering going to be deterministic then for any given data set? Or is there still some?
More or less, yes. Kind of the typical algorithms for how you compute the eigenvectors are secretly actually have some randomness in them. So that could have some random factors in there, but essentially it's gonna be deterministic. And you could there are variants of these that kind of get better partitions than they start with the Eigen partition, and then they do some random manipulation on top of that to get something a little bit better. So the basic form will essentially be deterministic, but kind of there's nothing that has to be deterministic about it. Yeah. So good. Okay. So we're going to get back to this. So the techniques in here, this is going to actually go through some stuff in dimension. So we're going to use some ideas from dimensional reduction, which will come later in the class, and we're going to also talk about a representation of data as graphs, which will also come later in the semester. Okay, so we haven't seen. We're going to spend time on both of these, and this really, if you look at the book, I put this as the one in the last chapter, one of the last chapters, because it's more natural and it's even easier once you've seen dimensional reduction and graphs before. It should be very natural after that. But if you haven't, I'm going to kind of review those, and this will also serve as an introduction to those areas, which might help you a little bit if your project will involve those. Okay. So we're going to go on a ride through dimensional reduction and graphs in order to get to spectral clustering. Although it doesn't necessarily need to use these are, I think, the right way to think about what's going on here. Basically, we're going to represent the data, turn it into a graph, turn the graph into a matrix, take the Eigen decomposition. Eigen decomposition reduces the dimension down to 1, and then in one dimension, it's easy to find partitions because you can just either cut it in the middle or do something else. Okay, so that's kind of the high-level theme that's going to happen. Okay. Okay, before we get into this, I just want to mention a couple things about K means and let's say also K and like the K medioid. Okay. Okay. So first one, how to choose K. Right. So this is something I think a number of you asked about, and I don't think I got around to the answer. We kind of ran out of time. And I said the first answer is there's not a good way to choose K, which is not very satisfying. Okay, so I'll give you an answer which is maybe a little bit more satisfying, but it's still not great. Typically, for in the assignment, I'll tell you what K is going to be. Sometimes because that will make sense for the assignment. Sometimes because it makes it a little bit more challenging. Just so you can see some of the challenges. Okay, but the other way of doing it is so what's called what's called like the elbow technique. Okay, and so what I'm going to do is I'm going to run the algorithm for different values of K. Right, so this is going to be 1, 2, up to, let's say, K equals 100, something large. I don't necessarily need to go up to 100 all the time, okay? But I'm going to run the algorithm for each time, and I'm going to write like the cost, and let's say the thing I'm trying to optimize, which I've defined these cost functions, and so for an x and the data set and some value of k. Okay, and so what is this going to look like? Okay, so for 1, it should be large, right? So if I have some data set which looks, so something like this, if I choose 1, I'm going to have to pick a center here, and I'm going to have to pay for all the costs of mapping onto this one point. So it's going to be large. And if I can pick 2, well, maybe it's going to be like this. Is the cost going to be larger or smaller? Right, so it's going to be smaller. Okay, so 2 might be smaller. And then if I pick 3, right, it's going to be here. Maybe 3 is on top of here, right? So then maybe the cost is going to be even smaller here, right? Okay? Then what happens if I pick 4? Right? I might pick, for 4, it might be like this. Okay, so it's smaller. It has to keep being smaller. So it's going to be even smaller here for 4, but it's not much smaller. Okay, and so what's going to happen is you're going to get this overall curve. It's going to come down, and it's going to kind of flatten out. So it's going to keep decreasing as k increases. And eventually, I've got 1 cluster for each of my data points. Okay? Okay, so if I look at this data set, what's the right value I should pick? Probably 3. Maybe 4 is okay too. Right? If I pick 5, I'm just going to, what's going to happen if I pick 5, I'm going to have to take some cluster up here, and I'm going to have to split this cluster into 2 parts. And okay, maybe I get a little bit more refinement on the data, but structurally it looks like it's kind of, it's like it's 1 group of points. With this one, maybe I split it into 2 groups, maybe it's 1 group. Okay? And so that means that the right thing is probably around here. Okay, so if I look at this plot, it's going to decrease sharply and then it's going to flatten out. And if I have cluster structure, it will kind of look like this. Okay, and so now, I can imagine that there's someone's hand at the end here, and it goes up and it attaches onto their body. Okay, and what's this right here? This is the elbow of the plot. Okay, and so if I can draw a plot that looks like an arm, I want to pick the elbow. Okay, so I want to pick the elbow of the plot, and that's why it's called that's why it's called the elbow technique. Yeah.
So if there wasn't an elbow and it was just a straight line, would that mean that there is likely not any clusters there?
Yeah, so it's still probably not going to be a straight line. Let's say I've got just a blob or a smear of points. I'm still going to get more reduction early on, but it's going to be less, it's going to look less like this, right? Yeah, so this is a good way of kind of looking at these plots might give you some sense of, is there cluster structure or not? If there is, I should get a steep decay and then it should gradual out. And how much is there really? And when is there clustering, when is there not clustering? You can kind of try and see it from this plot, but it's not even always so clear. Right? Even if my data is in really high dimensions, right? It could be, it looks like there's clusters even when there's not. It's going to look like a sharp decay, and then it's going to level out when it's not really clusters. It's just some weird things that happen in some high dimensions or some strange metric space I'm working with. Or maybe you say that does mean I have clusters if I do see a picture like this. Okay, so I mean it's kind of a vague answer, but this is, as you know, there are other ways people have measured this. This is the one I think makes the most sense. It's also not satisfying because I need to rerun the algorithm for a bunch of different values of k, right? So that seems, okay, if it was already a little bit slow, then it's going to be even slower. Now, if it ran fast, then, you know, then that's probably okay. if it ran in 10 seconds, I could run it 20 times, and it's not a big deal, right? So, okay, and if you can plot it, if you can plot the data in 2D or using dimensionality reduction techniques we'll see later in the semester, if I can plot it in 2D and I can kind of see, well, it looks like it's splitting a cluster needlessly into 2 parts, well then that's also might be a good indication. Okay. All right, so plotting is your kind of friend here. This is an exploratory technique often, and so if you're exploring data, you should try and plot it. Use everything you learned in the Viz course, right? These are complementary tools. Yeah.
So if you were using this elbow technique, so let's say you're like picking a random first cluster, would you want to use that same random first cluster again when you're running with k, like k equals 2 or k equals 3?
If I was worried about randomness, one run of these things should actually be multiple runs, and I take the best.
Yeah.
Right. So each one of these runs is actually 10 random restarts, and I take them one with the minimum cost function, because the cost function tells me which one of those runs was best. Yeah. Yeah. So, all right. Okay. So the second thing was something we did not talk really much about, was the K-medioid algorithm. Okay, and remember, this had a cost function from let's say x and a set of the clusters here was equal to, let's say, 1 over the size of x, just to normalize it, x times the distance from x to, let's say this is this set of centers here, so this set of the centers x. Okay. Okay. So this is the cost function. I'm using the sum of the distances, maybe normalized, so it shows like the average distance I'm doing. So I want to minimize this. So I want to minimize this, but such that C is going to be a subset of X. Okay, I'm going to restrict Kmeans Lloyd's algorithm, right, did not do this. It took the average of the data points, right, and that was the specific way to choose the center that minimized that cost function, which was the sum of the squares of the distances. This is just the sum of the distances. But I'm adding this constraint that it's a subset of the points. Okay, so like Gonzalez algorithm and Kmeans++, choosing the subset is something that makes the algorithms more general. It makes I can apply the algorithm more. So I can apply to more general x and d. Right, so if I have my data set as sets and the distance is the Jacquard distance between sets, I didn't know how to create an average. Right, how do I create an average of sets? It's not necessarily well defined. There are ways you can kind of try and define it, but then you have to compute these things. Okay, so finding the point that minimizes the sum of the distances is also one of those problems that's actually sneaky hard. Okay. And I actually asked you to do this in your the bonus question in the homework. It's kind of that problem is sneaky hard for a few ways, but you should try something. You'll get some points. But so I want to minimize sum of distances. That does not have a closed form solution. Okay, there's not. There are gradient descent based solutions that you can use, but they're kind of less satisfying than just taking the mean. For instance, the median doesn't necessarily generalize to higher dimensions, at least not in the way you'd want. Okay, so but if I restrict here, then I don't need to worry about computing an abstract, whatever kind of a vector in RD is my center. I can just pick one of the data points, or in fact, I can replace that step by, say, iterating over all the data points in that set, picking the one that minimizes the sum of the distances. So I can turn it into this combinatorial problem. Or I can pick a bunch of random points and see if any one is decreasing the cost from my old center. Okay, so I can come up with these heuristics, and there's nothing special about Euclidean space I need to use anymore. Okay, so if I don't have kind of Euclidean distance here as my distance and vectors here, then you'd probably use the K-medioid formulation. I could still run this with the squared formulation, but the squared was really only there because the mean then gave me an easy solution for how to pick the center. So if I'm not doing that, I might as well just use the sum of the distances. That's probably more natural. And it's going to be more robust outliers. Because it's not squaring the effect of an outlier, it's just adding with the rest of the points. All right, okay. So this is the last of the piece of the puzzle from the center assignment techniques. Okay, and this issue with how to choose K, there are going to be similar thresholds in just about any algorithm that you choose. Within the hierarchical agglomerative clustering was, when do I stop? When do I can again use K as the parameter, or I can use some threshold as parameter, and I'm going to get a similar plot here. Although maybe that distance is more natural somehow. And the similar thing's going to come up with spectral clustering. But now this is the top-down approach. Okay, good. So now let's get to spectral clustering. And so this is I'm going to present this in terms of my data is actually going to be input as a graph. The input to my problem is no longer just a point set and a distance. It's going to be a graph, and then I'll tell you in maybe about half an hour how to say, well, let's say I had a point set and a distance, and I wanted to run this algorithm. How do I do it? Turns out it'll be simple, but it's easier to first think about it in terms of graphs. That'll simplify our first approach on this process. Okay, so hopefully all of you have seen the concept of a graph before. Okay, you have a bunch of nodes and they're connected by edges. Okay, and we can store each nodes and edges in data structure in various ways, usually with kind of thinking them as objects, and you link them together with edges and so forth. So you can draw a picture of it. Sometimes the picture is kind of too hard to draw. If the graph is really big, I don't even know how to draw it in a picture. It may not be planar. I may not be able to draw it without the edges crossing. If it's a planar graph, that means there's a way to draw it without the edges crossing. But it might not be planar. Then I might just represent a set of vertices and a set of these edges. And this notation is very common everywhere, where I say a graph is a vertex set and an edge set, which is just a set of pairs. Notice these have no order on the edges. We'll talk later in the semester about graphs that have some direction on them. So I can go from, say, E to F, but maybe not from F to E. For now, we're just going to assume it's unordered. An edge means I could go either direction, for instance. Okay? So how many have not seen like a graph, idea of a graph representation before? Okay, good. Okay, so what we're going to use mainly, though, is a matrix representation of a graph. Okay, which is maybe a little bit different. I think of all the vertices. I can put these to label the rows and the columns, right? So if I look at, let's say this edge between C and D here, I look at, say, between C and D, and there's going to be a 1 because there's an edge there. If I look at between, say, G and H, there's no edge here, right? So if I look at G and H, then there's a 0 here. There's no edge because there's a 0, okay? So it's just this binary way of representing the data. If you notice, because it's symmetric, which direction it's going, that this one is also here, is also a 1, and this one is also a 0. Okay, because I can go from either the row and the column or the column and the row. So it's kind of it's duplicated information. I have no self edges in this example, so these are all zeros on this diagonal here. Okay. Okay. In general, for very large graphs, and we'll talk a little bit about this later in the semester, this is a pretty wasteful representation because typically the number of vertices grows basically the number of vertices, if that is n, then this is an n squared size, and the number of edges typically does not grow at a rate of n squared. It's probably something less than that. What less than that, we'll maybe try and talk about that. But so I'm going to have a lot more zeros than ones, so this mathematical representation will be a more compact way of representing it. Okay, but we're not going to worry about that now. We'll deal with scale and matrices a little bit later in the semester, and there are ways of dealing with this kind of naturally within the matrix format. Okay, and so this is I've drawn this diagram here, but really we'll think about it as a matrix. It's just this matrix that looks like the 0, 1 matrix. Okay, it's going to be n by n. If I have V, the size of V is n, then this will be an n by n matrix. Okay. All right. Okay. So if I have this, let me draw this picture up here again. A, B, C, D, E, F, G, H, and I've got these edges here. Okay, so now my goal is to find a cluster in this graph. Okay, and I told you that that within this spectral clustering, the big idea was this top-down approach, right? So I need to take one data set and split it into 2 data sets. So I really only need to find 2 clusters. I'm going to split the graph up into 2 pieces in the best way possible. So I only need to worry about finding 2 clusters, and then I can recursively apply this. Okay, so I just need to take this graph and split it into two clusters. And so the way I'm going to think about this is that, okay, so what do I mean by splitting it? I'm going to split the vertices. Okay, there's ways to think about splitting the edges, and they're often actually just variants on splitting the vertices through some transformations. Okay, so I'm going to split V, the vertex set, into S and T, where T is going to be V set minus S, so it's the complement. So I'm going to split it into 2 sets, S and T. Okay, so I'm going to think about splitting that, and I'm going to use the edges to somehow measure the split. So, and then I'm going to use the edges E to somehow measure how good the split is. Okay? So the edges are somehow going to play the role of the distance before and the vertices of the data set points. Of the data points. So how do I measure how good of a split? Right? If I choose a split, how do I measure how good the split is? Right? What would be a good split? So what would be a good cost of a split between S and T? So let's say I'm given a graph, which is implicit in this definition, and then I'm given a split into S and T, which are 2 subsets of the vertices. How do I measure this cost? Yeah?
Would be maximizing the resulting edges.
So I want to maximize the edges.
Yeah, so cut the least number.
Oh, so cut the least number of edges. Yeah, good. So I want the cost to be low, and then, so one idea of the cost is just the number of edges in E such that where E is going to be a vertex set V1, V2, where V1 is in S and V2 is in T. Right? So this would be, what I would do is I would describe this as the cut of ST. Right? So this is the definition of the size of the cut. Okay, good. So I want to make a cut that's as small as possible. Right? So how would I do that? I probably say this set A, B, C, D is S, and E, G, F, H is T. Right? It only has the single edge here, which is cut. Right? So if this is S and T, then the size of the cut is going to be equal to 1. Okay? So this is good. This is probably the cut I would like to make. This is probably the cluster I would like to make. Yeah?
There's what, so going from F to H edge, with this definition, what's the difference between making that cut and then making a cut on F to H?
Yeah, so that's actually the problem with this definition. This is a good first thought, everyone's first thought, but it's not always the right thing to do, right? And this is because there exists another cut here where I can do S prime and T prime here, which also has the cut of S prime and T prime is also 1. Okay, so I can also split H off from the rest of the graph, okay, into T prime and S prime, right? And this has the same score on the cut. The first cluster seems better, right? But these second sort of clusters are actually, that I could do, is actually pretty common. If I look at large graphs, this is under even like the very basic model and in real world graphs all the time, you get a lot of these nodes that have exactly one edge connecting to something else. Maybe a big super agglomerate or just kind of another small thing. And so this would be a valid cut. This minimizes this cut metric. Yeah?
If you had done 2 cuts, let's say we went from k equals 2 to k equals 3, would this be a bad cut? I mean, H might be an outlier, but Jason would be happy for it to be separated from the rest of the cluster that it was kind of connected to.
Yeah, so, you know, if I'm doing 3 cuts, then maybe this isn't so bad. But what happens in these large graphs is there may actually be kind of 2 big pieces that maybe they have 5 edges between them, and they're going to be like 100 or 1,000 vertices that have 1 edge to the rest of the graph. And so then the best cut is just going to be pulling off all these vertices, and I'll just be doing that endlessly, not really uncovering the structure of what's going on here. You want to add to that?
Oh, so could you choose the cut that would minimize the maximum size of the cluster? Or
Yeah, good. So what I want to do, and your intuition is right here, I want to somehow make sure the cut is like balanced, right? And one way of doing that is to, you said minimize the maximum size. It's usually thought of slightly differently, which is to maximize the minimum half, right? Right, so the problem is the minimum half, T prime over here, is only of size 1, which is pretty small. I want to ensure that the minimum half is at least so big. Right, this makes sense. If I'm building a hierarchy, I want it to kind of be even. Just like in data structures, you want a balanced binary tree, not just any binary tree. The balanced binary tree tells you kind of the depth is bounded. There's lots of advantages to this. Okay, so I want to do something called the normalized cut. Okay, so instead, so what we typically want to do is what's called the normalized cut instead. And so I want to introduce this other thing that's typically called the volume of S. Okay, and the volume of S is also going to be measured by the edges again. Okay, this is going to be the number of edges with at least one end point in S. Okay, so if I go back here, the volume of S is going to be 1, 2, 3, 4, 5, 6. I count the one that's only half in, right? So the volume of S is equal to 6. The volume of T is going to be equal to 1, 2, 3, 4, 5. Okay, and the volume of S prime is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the volume of T prime, as we recall, is going to be equal to 1. Okay? And now I can define the normalized cut of ST. And so there are a few ways that would make sense to do it. I want the cut to be small, but the volume of the minimum size to be large. And so the most common way and the way normalized cut is defined is going to be cut of ST over the volume of S plus the cut of ST divided by the volume of T. Okay, so now if either of these is small, then it's going to blow up that term in the sum. Okay, where if these are large, it's going to be smaller here. Okay, so if I look at this, the cut in terms of ST, right? So remember that the cut was the normalized cut of ST is going to be 1 over 6 plus 1 over 5, which is going to be about what is it saying in my notes? About 0.367, whereas the normalized cut of S prime T prime is going to be again 1 over the volume of S prime, which was 10, right? So this term is smaller than before, but this is now 1 over 1. So this is going to be about 1.1. So this normalized cut of the thing that just took off the single term is going to be much larger than the one that split them pretty evenly. And so probably even if I had two edges going in between, even if I doubled this would still be a better cut than taking off one piece. Right? So even if I put a 2 in the numerator here, that would double this value. It's still less than 1.1. Okay, so I can handle a few more edges in here, and it could still be a better cut. Okay, and so this is the measure that you typically want to find as the best way to split things, and this is what the community has kind of settled upon. Okay, and we'll describe an algorithm that kind of corresponds mostly with optimizing this measure. Okay, so now, given a graph, right, how do we, in this small graph, there's kind of obvious things to try, right? But if we're given a very large graph with, even 1,000 nodes and 10,000 edges, this seems like it might be more challenging. What are all the things we're supposed to check? Right, there's a huge number of combinatorial choices of things we can check in this graph to split it, and so it's at first thought it's like not obvious. How do I possibly do this? I can try and do if you've taken an algorithms course, you can find like finding the max flow of a graph is kind of something you can solve for, but the min flow is going to be harder to solve for. Okay, but you can find the max flow and the min cut is the the min cut corresponds with the max flow, but that's the wrong measure. That corresponds with this, which is not stable to these little outlier points here. Okay, so for the normalized cut, this becomes a little bit harder. Okay, but these spectral methods, which we'll talk about next, are going to give us a way to do this. Okay, so let's go back to this graph representation and the matrix representation of the graph. Okay, and so I'm going to actually describe now two matrices which are going to be kind of useful here. One is the adjacency matrix, which is what we walked through before. There's a 1 if there's an edge between, this is D and B, right? D and B have an edge, there's a 1 here. Okay, this is one we talked about before, and this is the degree matrix, which is all zeros everywhere except on the diagonal, right? So the only point of interest is on the diagonal of this matrix. And so, for instance, this node corresponds with C, right? If I look at this node for C, I see it has 1, 2, 3 edges coming out. That's the degree of this vertex is 3. Okay, so I'm just recording the degree of every vertex on the diagonal of this matrix. Again, super wasteful, but we'll use it for the linear algebra properties. Yeah?
I don't know if you already covered this or not, but how do you convert your set of points to a graph?
Yeah, so I have not explained that yet, but I will get that. But for now, some people use this directly on graphs. So let's just think about for graphs now, but then it'll be, turns out it'll be straightforward. Okay. Okay, so we don't want to use either of those, the degree or the adjacency matrix. We want to use what's called the Laplacian matrix. And there are different ways of defining what is the Laplacian matrix. I'll talk about two. I'll start with the unnormalized Laplacian matrix. Sometimes it's just called the Laplacian matrix. And that's just D minus A. The matrices are both n by n, so I can subtract one from the other. And so the adjacency matrix had all zeros on the diagonal, so the degree is still just the diagonal matrix, and then the off-diagonal part are the negative of the ones if there is an edge there. Okay, so this is just kind of combining these two matrices together. This is called the Laplacian matrix. Okay? And this is somehow capturing the importance of nodes and the connectivity of it. Okay, and it has kind of this property that you can think of it as, I have some water flowing into the degree, and I'm going to, so it's size 3, and it's going to flow out with a different sign into these 3 different ways, right? So this is A, and it's going to have, some 3 flowing out. And this is kind of how to think about this. This is describing some flow going on, and we'll revisit this later in the semester. Okay, and so what I want to do, I want to take this matrix and I want to do the Eigen decomposition of this matrix. Okay, I assume you're supposed to all have, told you all to have linear algebra before taking this course. Okay, so we're going to do the Eigen decomposition. If you have not done this before, it's built into every kind of language that can handle matrices. In Python, it's kind of just one line. And what you're going to get out, you're going to take an L0, I'm going to call, say, Eigen or something, which is the command in MATLAB, and it's going to come out as these two matrices. I may have mixed up the order, okay, but I'm going to get, or let's say, depending on lambda, V and lambda. Okay, and so V is going to be these eigenvectors, which I've written here, and lambda is eigenvalues. So these are the eigenvalues, and these are the eigenvectors. Okay, and so this is the first eigenvector is going to be not useful to us. This is useless. Okay, it's always, for the unnormalized Laplacian, it's always going to be 0 up here. For anytime I create the unnormalized Laplacian of an undirected graph, it's going to be 0, eigenvalue, and the eigenvector is going to be all the same. doesn't tell us anything. Okay, if you've seen PCA, this is kind of like the centering part of PCA. So it's not really telling us something about the structure of the graph. The second one, or in general, the first one that doesn't have a 0 here, is going to be the interesting one. Okay, this is called the Fiedler vector, or actually that's the vector part of it. And this value tells us how useful it is. The smaller that value, typically the more powerful this matrix is going to be, the better split we're going to get in some sense. That's a good indicator of that. It's not completely the same thing, but it's a good indicator of that. Okay, and this gives us this vector here. Yeah.
So the Fiedler vector, is that just the smallest non-zero eigenvalue?
It's the eigenvector associated with it's always the second it's always the second eigenvector. In general, we want to look at the first one that has a non-zero eigenvalue. For instance, if the graph is not connected, then the second one will be 0 also. Then the third one will be interesting. Okay.
So the ordering of these.
Yeah, but the ordering is going to be from typically they'll give you out in the right order, sorted by eigenvalue, depending from smallest to largest or largest to smallest. But in here I've written them from smallest to largest. Okay, and here the smallest one is most interesting. In SVD and PCA, when you're looking at singular values, you typically want the largest one. Okay, but because we did, remember we did D minus A, so we're subtracting the adjacency matrix, so this ends up being the smallest one we want. It's a different representation of what's going on here, because we're looking at the Laplacian instead of the original adjacency matrix. Okay. Okay, so we're going to take this Fiedler vector, okay, and this is going to encode, without even understanding how eigenvectors and all this work, we're just going to take this vector, and this is going to give us all the answers we need. Okay, what this tells us to do is how to embed the graph into R1, into one dimension. I'm going to embed the graph the best way possible into one dimension, and in one dimension it's easy to find a cut. Okay? Okay, so what I've done here is let's go and try and work through this first, okay? Just in one dimension here. And remember, these rows mean something, right? So this corresponds with A, B, C, D, E, F, G, H. These actually correspond with the vertices, and I've basically given a one-dimensional value for each of the vertices, right? So I'm going to embed these on top of each other. So let's say if this is -1 and this is +1, then let's embed these on here. So -3.6, this will be A, -4.2, this will be B. C is going to be -0.2, maybe it's even. Okay, so this will be C. It turns out D is going to be right on top of A. We'll get back to that. And then E is going to be over here. F is out here. G is out here, and then H is out here. Okay, so if I just wrote down these coordinates, I'm going to get them in this one-dimensional ordering. Okay, and then how do I find the split? I'm just going to, the simplest way, there are two ways to, once I've done this, there are two ways to find the split. So one is I'm just going to split at 0. Okay, everything on the left is one cluster, A, B, C, D. Everything on the right is the other cluster, E, G, F, H, which is exactly what we wanted, right? That was the one we identified as the best split, right? That happens right here. All of these are negative, and all of these are positive. Okay, so it just happened to give us this embedding. Okay, the other more advanced way, which for more complicated graphs turns out to be a bit better and doesn't really, asymptotically doesn't cost any more, is the second way is I want to scan from left to right and maintain the normalized cut. So if I scan from left to right, first S, the set S, kind of, right, I want to have this split where S and T, and where S is, only contains B and T contains everything else. I can compute the normalized cut, and then as I scan from left to right, I'm keep increasing S and decreasing T, and this is as fast as just reading off the edges on the graph. I can easily maintain the normalized cut and find the one that minimizes that value. Okay, this occasionally happens. For instance, you can sometimes get some graphs where 0 is here, but if I look at the data, I've got a bunch of data points out here, and then another bunch of data points that look like this, where there's one of them that just crosses over 0, then I'd like to make the split like this. Or there's kind of this separation between them, and it turns out that if there is a good split, which is a little bit more imbalanced or something like that happens, I'm going to maybe have something cross a little bit over to one side of 0, but I want to have it with that whole side of the cluster. And so for more complicated graphs, you probably want to do this scan approach. It's a little bit more complicated, but not that hard. Although splitting on 0 usually works pretty well still. I would have been pretty close to the right answer here. Okay, and I mentioned, you asked about randomized algorithms. Sometimes you start here and then you look at the graph and you randomly try and move edges, vertices on one side or the other across the split. And doing that a little bit can often give you a little bit better answer. And so the actual best algorithms for this do some extra randomization on top. It's too big to try everything, but with a little randomization, you can often do pretty well. Yeah?
Could you just find the mean of the Fiedler values and then use that?
Yeah, so I think this is, no, this is not, yeah, it's not always going to be the case that the mean is 0. But it's often going to be the case it's pretty close to 0. You could try doing that, but it's more complicated than doing a split at 0 and asymptotically the same as doing the same scan, because it costs less. The scan costs less than actually computing the eigenvector. So you might as well do that instead. I don't know of any kind of theoretical justification for doing that. You could try it, but I don't think it's going to improve upon this. Can't improve upon the scanning technique. So if you can do something more complicated, you might as well do that. Yeah.
So recursively, you wanted to split both those again. You have to recompute the Laplacian matrix for the
yeah. So that's what you should be doing. There are other ways to do it, and let me draw this picture. And like you could think of automatically using the first two directions and then splitting using both of those into quadrants. Right? I could have now I've taken the first or the second and the third eigenvector and I've drawn the picture accordingly up here. Right? So I've drawn the two-dimensional coordinates now. This is a two-dimensional nonlinear embedding of this data set from the graph. And what I can do is I could define a two-dimensional base clustering into 4 pieces based on the quadrants. And what I'll get is this is 1, this is 1, this is 1, and this is 1. This would be the 4-way clustering, which turns out pretty well in this graph. There's not really a better way of doing this. You want H to be on its own because the cut size is small, and C is closer to these other ones because it's the one connected to the other side, right? It's the one that has the cut where A, B, and D are safely on the far left side of this joint. Okay. Right. So, but kind of what you're kind of this would kind of be like a shortcut, which might work fine, but doing this too many times, there's some splitting things along the axes is going to produce some empty clusters and some weird other variants. Whereas if you do this recursively, it'll give you a better structural clustering. And you're probably only going to do this a few times, and so the cost is not too high to do it kind of from fresh recursively. Yeah.
So here we're just going down the axes and trying to cut them and then see which one.
Well, so if I looked at this whole subgraph, A, B, C, D, right, I would just take that subgraph of just those 4 vertices and do an Eigen decomposition on the corresponding Laplacian matrix for that. That's kind of, in principle, what you're supposed to do this hierarchically. I want to kind of do this recursively, so once I do a split into subgraphs, I'm going to ignore everything else outside of it. Yeah, but I've lost information that C and E are connected together if I do that. So this incorporates that. But in kind of more complicated graphs, the recommended thing seems to be to just do this recursively, ignoring this information, because that might confuse things. Okay, but there are some advantages as well. Yeah?
Is there a case where we get the first cluster as A, B, C, D, and in the second iteration of clustering, we would want to cluster C and E together, even though in the first time they were separated?
So when I'm doing assignment-based clustering, I'm just finding the best clustering for that size K. When I'm doing a hierarchical version, either top-down or bottom-up, once I've made a decision, I'm kind of stuck with it, at least within that algorithmic paradigm. Okay, so if I want to just say, I want to find the best 3-way clustering of the data set, or the best 4-way clustering, the best 4-way clustering might put C and E together in that cluster, but this is a pretty hard problem to solve. Kind of combinatorially looking over all possible, sets into 4 groups is this really big search space. And so these are kind of restrictions we're using to help us kind of prune down that search space into something feasible, right? So ideally, you might want to do something like that, but within this paradigm, I'm going to not let myself do that, just to make it so it's tractable. Right? Yeah. So that's a good question that could come up, but this is a shortcoming of this framework. Yeah. Okay. Okay, so the other thing I'd like to mention here is that, look, A and D, in these first 2 dimensions, and this will go up until the very last dimension, they're right on top of each other. Their coordinates in the eigenvectors are exactly the same here, right? If I look at A and D, they are exactly the same. This is not an accident. If I look at them in the graph, their connectivity is exactly the same. They're both, A and D are both connected to each other, and B and C and to nothing else. So if I just look at the graph, I can't distinguish them. All I know is the connectivity information. So, okay, of course it's going to give them the same spot. So this is kind of, it makes sense it would do that. And it's going to be hard to separate them into different clusters because they're reacting basically the same way. Yeah?
Random question. Does this approach change at all if you have a directed graph, or does it work?
Yeah, so there have been different groups that have tried, different papers that have said, what if I have a directed graph? What's the right thing to do? And there are a variety of approaches that try and do that. They almost always, if they seem to be working, they almost always seem to be working about the same way as if I remove the direction within clustering. And this was not what people thought initially. They thought there would be some different clusters you'd get out, and that turns out that the right thing to do under different kind of well-reasoned mathematically thinking of the right thing to do, turned out to be almost identical to just, or sometimes identical to removing the direction. Okay, so for directed graphs, I would just remove the direction and run this out. We'll see stuff later in the semester where the direction will be useful and important. But at this point, it turns out it typically is it does not tell you something different about clustering. Yeah. Yeah.
So I'm not really familiar with the like graph style. But wouldn't the directed graphs be representing another type of data or another type of like behavior in the because it's a whole different like story if you're just
yeah. So we'll spend several lectures thinking about what a directed graph represents as opposed to this. It means like if you have a direction from G to F that I can get from G to F, maybe with some probability or with some amount of traffic flow, so something like that. But if I can get from one directly to the other and I cannot get from G to H to the other, well, it means these are still close in some way. And the direction, so this was not obvious when people started thinking about this problem, but if eventually you think hard enough and do enough experiments, you eventually be able to convince yourself that the direction turns out not to be important for these sort of tests. In most ways of formalizing it.
The reason I asked was because, so do we use this method for directional graphs then, or should we not?
Yeah, so people use it, and it can be useful to do that. But the right way to do it is what, if you trust me, is to just remove the directional information. I can point you. I can dig up some papers and point you some papers offline if you're interested. But yeah.
What about for weighted graphs? Would it be the same?
Okay, good. Okay, this will go into the next point, which is another point you've been asking me about. This is how to get to weighted graphs. It depends on what the weights mean. Okay. Okay, so I want to kind of generalize this notion of the adjacency matrix to an affinity matrix instead. I'm going to say A is going to be a n by n matrix with real numbers now instead of binary numbers. And so this will correspond to, so I'm going to say that this is the vertex set, but this is actually going to be equal to my data set, and I'm going to be given instead instead of edges, I'm going to be given a similarity function, S, which goes from, okay, so instead of a distance, I have a similarity, right? This similarity is going to map, and let's just say that it's going to map from AB to something in 0, 1. So it's going to be one of these 0 to 1 value similarities. You could use a generalization, say with dot products and so forth, that's not 0, 1, but let's just say it's in 0, 1. Okay, and so then this matrix is going to be n by n, and let's say I have some value b and g down in here, and then this cell is going to be the similarity between b and g. So I'm just going to compute the similarity between b and g, and that's going to fill in the cell. It's going to be a real value here between 0 and 1. Still an n by n matrix. I can then define the degree matrix here, and again, a cell, it's called d II, is going to be, I can write this as the sum of I equals 1 to n of the similarity between I, let's see, and j 1 to n, similarity between nodes I and j will be the similarity, and these are all zeros again. Okay, so I can define this in this way, and then I define the Laplacian, the unnormalized Laplacian, as d minus a, but just use the affinity matrix and this generalization of the degree as replacements, and everything works the same way. Okay, so this is one way of assigning weights, one interpretation of weights. This would work fine if the weights were bigger than 1 as well. You know, it's just the linear algebra all goes through the same way. What this says, this interpretation of the weights says that a larger value means they're more similar. Maybe there's more flow in between them. So there's a highway in between two parts of the city. Those are more well connected. If I wanted the weight to mean that that's a bigger distance, well then I kind of have the issue if the graph is not complete, right? There are missing some edges, then those effectively have a distance 0, and that means that they're really close, which is not typically what I want in this representation. So it makes more sense to have a larger value mean they're closer. And in that sense, it goes through fine with weights. But that's the modeling to keep in mind, and you can do this general affinity matrix, so as long as you have a data set and a similarity function, I can run this algorithm. Okay, now there are some tricky things. If the similarity is not associated with the metric distance function, then this matrix, the Laplacian, may not be a positive definite matrix, and then some of the eigenvalues will be not real numbers. So you might want to be careful. Typically, the second eigenvector will still have a real number, and this will all still effectively work. Okay, so you can still probably run the algorithm, but you might need to check in case the second one is not real, which is pretty unlikely, but it should still generally work. The kind of what does it mean behind that? It's less clear, okay, what's going on, but you can mechanically run the algorithm and it may work fairly well. Okay, so this is one deal with weights and generalized to point sets, and not distances, but similarities. Okay, so this makes it actually a fairly general algorithm. The expensive step is computing the eigenvectors, but then you just do that some small number of times until you get enough splits and you're satisfied. Okay, so once you have a similarity, you can do this. But this is again a bit more expensive. I have to compute this n by n matrix, which is at least n squared time. Right, and then it costs a little bit more on top of that. Maybe if I only need the second eigenvector, that only takes I can do that faster than computing all of them. But it becomes at least n squared if I do this. So for very large data sets, for now it's slow, although we'll look at ways to potentially speed this up, although not necessarily for this problem. Okay, I'm gonna do for the last 3 minutes, do a little bit of the switch part of the bait and switch. Turns out the unnormalized Laplacian is not the right definition of the Laplacian to use for the minimizing the normalized cut. There's something called the Laplacian or the normalized Laplacian matrix, which is the right thing to do. It's a little bit more complicated, so let me just go through it quick. Some of the structure looks a little bit different. The Laplacian I showed is still used in many places. That's not wrong in all cases, but for normalized cut, you want to use this regular Laplacian instead. Okay, so I need to do a matrix to a power, and in fact, the power minus 1/2. And that's just, when it's a diagonal matrix, that's easy. I just take all the terms on the diagonal and I raise them to that power. In this case, 1 over the square root of the value. Okay? And so then the normalized Laplacian is defined here. Right, see it? It's I, the identity matrix now, minus D to the minus 1/2, A, D minus 1/2. This is, right, so this actually, basically what I'm getting is now every, yeah, it's just a different way of normalizing the flow in the matrix here. This turns out this is equal. This is equal to d to the minus 1/2 of the normalized Laplacian d to the minus 1/2. So I'm basically normalizing the values on each node by its degree. I'm saying if it has a really high degree, that doesn't necessarily make it more important in the clustering, which was implicitly what was happening before. Those are getting spread, high degree ones are getting spread further apart. And I don't necessarily want to do that. The ones which have low degree, those I want to push far apart. I don't want those to kind of accidentally cross over the graph. Okay, and this tends to force the things kind of naturally that have low degree further apart. I'm essentially dividing the negative signs like an inverse is kind of like I'm dividing through by the degree. And I have to split it on the left and the right so it stays symmetric. If I only did d to the minus 1 on one side, it would no longer necessarily be a symmetric matrix. So I'm splitting it into two parts. Intuitively, that's what's going on. Okay, but linear algebraically, I can just do that operation instead of the previous one, not that much harder. Okay, and I still get eigenvectors. This one's still 0, but this is not necessarily all the same. I still want to look at the second one here, and this one, the second one, still gives me a one-dimensional ordering. It turns out this is a little bit better. Now I've scaled the ordering by this. Scaled by 1 over lambda I. So I've scaled by 1 over the first eigenvector, which is technically what you're supposed to do, the best embedding of this. And what's happening is this is even more spread out across 0. This is kind of telling me it's an even better cut. These two are A and D are still in the same spot. H, I guess, gets wrapped around here a little bit. Okay, and this is giving me a slightly different cut if I tried to do 2 at the same time, but I really only care about this here. F seems to be the furthest away, and again, C and E are closer. Okay, so it's giving me a slightly different cut than before. This one will tend to give you a better one-dimensional embedding for the normalized cut. For other things, you want to use the other embedding, but for this, you want to use this. And it's just a small change. Okay, great. So let's stop there, and we'll talk about streaming algorithms, which are really big scale algorithms. Ideas of that on Wednesday.